Okay, good morning, everyone. The record is on, so let us carry on. Okay, right. We have to learn about the thing that we can call the influence line. What is it? Normally, when you design a structure, there are two things you need to consider. First, it's sort of hidden somewhere in the class. You will be exposed to it predominantly in the next semester. That would be the load combination, because there are so many kinds of loads that can, be imposed on your structure. For example, date load, live load, wind load, earthquake, water, flood, and fire load, and so and so. And those loads, they cannot possibly occur at the same time. So you could, for example, you cannot expect the earthquake, the maximum earthquake, to occur at the same time as the hurricane or the flood. So we need to handpick to find the say practical or realistic combinations of load that will occur to your structure, because you cannot throw everything at your structure and try to design for it to survive. That would not be very economical. So one thing is that we need to find the proper load combination to put on the structure and make sure that your structure will survive those combinations. The second is the locations, because some of the loads do move. So you need to find the locations for the loads to, to see which locations of the loads that you place on the structure will give you the worst case scenario. Okay, so because the load can change location, so we have another analytical tool to help us figure out the maximum force on the structure, and that tool we call the influence line. Okay, so we mentioned load combination, and the location is the placement of the loads that move. Okay, you can see that we have all kinds of moving load. For example, you can see now that if you have a crane, you see the hoist can move. So we can have a moving load here. See, the screen is pretty slow. All right, and this is the small tool that I can use to help move the stuff. I think I have the problem with the internet already, so you guys can please hang in there. Okay, so it's back now. Good. So, we can use this stuff to help move the load, or in the, you can see we have something like this in our lab as well, right? It's called the moving crane. We used to move the stuff. So this beam is moving on the support here on the rail. So you see the yellow beams become the moving load on the green beam on the rail here. So when you design these rails, you need to know the placement of these yellow beams that will produce the maximum moment on shear and so on the green rails. Okay, and likewise here. And we can also have the huge structure like this, and you can see this is pretty big, and it used to move the cargo in the area. I'm trying to locate a human being in this picture so that you can see how big it is. But but you can see in this one, that's a human being. You see that? The green dot, that's a human being. And this is a structure that move the crane and stuff, move the cargo and stuff. So it's real. And look at this. This is probably 3 or 4 meters in depth. Just look at the size of human being. And the design to move the loads. And they are called gantry, And this is a launching truss. You probably have heard of the word before. When we construct the train above the ground, sometimes we call it a viaduct, to place the structure for the train like that. You can see that, right? in order to install the segments of those structures, we use the moving truss or launching truss rather, sorry. So you can see from this diagram here that the truss will launch itself out like this, and then the blue portion will move in pursuit. And then when the blue portion reaches here or here, they drop the segments to create this new portion for your structure. But we need to have the launching truss, and it will move along the piers that have already been constructed before that. See the piers here, and so these are the piers. And we are still having a lot of this, you know, under construction of all kinds of the SkyTrain that we now have. That's a launching truss, and this is like a mega structure, you know. And of course, the loads move in these structures. You can see this too. Now that's this is a segment of the structure for the train. You can see that's a launching truss. You can see here the launching truss, and you see the size of the road underneath it. Okay, so it's pretty huge. So you can see the segment will move, the loads can move, and some of the loads will move. So we need to introduce you to the new stuff that is called the influence line that can be used to help design these kind of things. And of course, the most common moving load is the car, right? See the cars. This is the Golden Gate Bridge. This bridge, I don't know what it is, but yeah, you can see. So to design the bridge, for some of you who dream to become a bridge engineer, you know, you have to deal with the moving loads. Okay. So with that said, all right. So when the loads move, the placement of the load or the location of the load becomes very, very important. And we are going to have to use the influence line to help figure that out. Okay. So we can start off by considering, you know, two people carrying a bucket of load, and this maybe you can move this bucket of load around. You know, it doesn't have to be in the middle, and maybe getting closer to one guy or another. So now what I'd like you to do is just I'd like you to swap to see this. Okay. Now we are going to investigate the change of design function, reaction, shear force, and moment of the beam when we have the load that moves from A to B. When I say A to B, I don't have A, B here. Okay. So let's say we have the load like this, and then we have the beam, just a simple beam. So you may view this two support as two people carrying a basket. Stuff, you know, and this basket moves around. So let's say when the load P is right at the support A like this, so roll on the left. Okay. When your load P is right here on the left support, what would be the reaction, or what would be the load that person at A has to carry? Of course, when the load P is right here, I should say when P is at A, okay? So you can see very clearly that like this, the reaction at A is P, right? And therefore the reaction at B becomes 0, obviously. So now, because we are talking about the moving load, so I'm just going to start moving the load around, right? So now let me move the load a little bit further to the right. Let's say P now is at the location 0.1 L. We move the load 10% of the length of the beam. Okay. So what happens now? You can take the moment to find a reaction But you can also look at the ratio of the placement of the load and the beam. You can see that, okay, this is 10%. So now you should know that this reaction is 90%. And this is only 10% of P. Okay, you follow? I can still move the load further. Let's say 10% more. Now the load is at the location 0.2 L. Now when the load is at this location, it means that this reaction would be 0.8 P. This would be 0.2 P. You can see when we move the load, okay, the magnitude of the reactions change. And I can also move further. Say 0.3, okay? Let's say if this length is 0.3, I move it 30% of the length. So now you should be able to guess that this reaction is 0.7 P and this is 0.3 P, right? I can move it so on and so forth. I can continue to move, let's say until it reaches the midpoint. Or mid-span. When I reach when I reach mid-span, that's when my load is, equal, right? My reaction is equal. And when I start to move, beyond the midpoint of the beam, let's say now for the sake of demonstration, my P is at the length of say 0.7 L. When I reach this, you would know that this becomes 0.3 P. This becomes 0.7 P. And so on and so forth until I reach the opposite end or point B. When my P is here, you know that this becomes 0 and this becomes P, right? So from this, I can now gather up the information, okay, from this, that when I'm going to plot the magnitude of the reaction at A in Y axis, okay, and the location of this load P in X axis. So when my P is at 0, my RA is equal to P, right? When I move to location 0.1 L like this, my RA is 0.9 P. When I move it to 0.3 L, 0.2 L, I'm sorry, 0.2 L, now I have 0.8 P. And when I move to 0.3 L, this is 0.1 L, right? This is 0.2. When I move to 0.3, I will have RA equal to 0.7 P. Can you notice the linear relationship that we have? I can continue to plot the value, and then I will have a graph that looks like this. Okay, now this is the graph that shows the value of the reaction at A according to the movement of the load. When the load is at the location x equal to 0, or I should say plainly that when the load is right on top of the roller, the reaction RA is equal to P. When I move the load to this location, 0.1 L, 10% from the roller, the reaction at A, at support A or the roller, is equal to 0.9 P. When I move the load to this location, 0.2 L from the roller, now I have the let's see, 0.2 from the roller. Now I have the reaction equal to 0.9 P. And to 0.3, I would have 0.8. And then, I'm sorry, 0.2, I have 0.8, right? And then 0.3, I have 0.7. Okay, it's a little bit off. So let me clarify that. 0.9 is here, 0.8 is there, and then 0.7. Okay, so on and so forth. And until I reach midspan, I get 0.5. And then when my load reaches the hinge at the opposite end, like this, I have the reaction at A equal to 0. See, the values of the reaction at A plotted in y direction along with the location of the load. Okay, this is what we call the influence line of RA, influence line of the reaction at A. You can see that you can, when you have the load acting anywhere on the beam, you can use the influence line to obtain the magnitude of the reaction right away. Now, one more thing, when we create the influence line, we don't create by using the load P like this, you know, sort of troublesome. We would create with the magnitude of the load equal to 1. So if I change the load P from P to 1, this plot, the influence line of RA, simply becomes like this. I can just replace RA, I'm sorry, I can just replace P with 1. And when I replace P here with 1, like this, I should use a different color, right? This, if this is 1, you know, all the P terms are gone. Like that. Okay, so now you are going to have the influence line of reaction at A with the value based on the unit load. So here is 1. Okay, and I can do the same instead of plotting the values of RA, I can also plot the values of RB. And you can see the influence line of RB will be just opposite of the influence line of RA. That value is also equal to 1. Okay, is there any question? This is too close. Let me okay. And let's say if you have the P at the location, say 0.4 L, you can just come here and okay, if we are at the 0.4 L, we can just, okay, RA would be 0.6 and RB would be 0.4, just like that. Okay, but that's not it. We can also create other design functions out of this. For example, I can also calculate, let's say the moving loads are the same, but instead of showing just the values of the reactions, I can also investigate the shear and the moment, the change of the shear and the change of the moment rather, on any location of the beam when the load moves from A to B as well. So I can say, now I'm going to try to calculate. I'm just going to try to find a way to manipulate this. So, okay. Let's say from the same beam, now I want to know the shear and the moment at midspan. Okay. Now, when I place the load P or the moving load, maybe I should write them from anew. Okay. So let's say here's the same beam. Now I place the moving load here. Okay. What would be the shear at midspan and the moment at midspan? But the first case is pretty easy. Shear and the moment, they are 0, right? Because the load just lands on top of the support. So you would have neither shear nor moment at midspan. So let's move them around. Now, if I have the unit load here at the location 0.1 L, okay? So now we know that here is 0.9. Okay. Now, if you want to know the shear and the moment at midspan, allow me to cut the free body diagram by removing this. Okay. And now that doesn't look like 0.9. So here is 0.1. Okay. And can you calculate the moment? This is going to be the positive moment, which is going to be equal to 0.9 multiplied by 0.5 L minus 1 multiplied by minus 1 multiplied by 0.4 L, right? It's huh? Okay. That's 0.05 L. Okay, I can also move it. So now you know what I'm getting at. See, at the location 0.2 L. So when the load is here, I can in fact look at the reaction from here that, okay, my R at 0.2 L IRA is 0.8. I can just take it from the influence line and know that this is 0.8. And now this is upward, right? Now this is 0.2, obviously. And the moment is also 0.8 multiplied by 0.5 L minus 1, now multiplied by 0.3 L, right? It becomes 0.10 L. And now I can move it again. To 0.3 L. Now I have 0.7. I have 0.3, and my moment becomes 0.7 multiplied by 0.5 L minus 1 multiplied by 0.2 L. This becomes that correct? Pretty confusing. Hang on. Yeah, 0.15 L until I reach the special point at 0.3. Excuse me. Look good. Let's move this a little bit and write the at symbol. At midspan. Okay. Now the shear is right at that location. So now we have 0.5 here, right? At midspan, that's the reaction. This is also 0.5. Okay. Now the moment. The moment is now 0.5 multiplied by 0.5 L minus 0, right? Because that's a moment at midspan. So it becomes 0.25 L. So you can now see that I can take all these values and plot. But before we do that, let me try to get this into your head. You should be able to do this since the day of statics, but I kind of doubt it. You look at the shear at midspan. This is special because we have the point load just right on top of the location where we want to find the shear, right? So the shear value, at this location, slightly to the left of the unit load and slightly to the right would be different. Okay, if you draw this free body diagram slightly to the right of your point load, and if you draw it slightly to the left, they would be different. Okay, so let's try to plot the influence line. I use the blue, but this is green, so let's use the green. Okay, so the next is the influence line of the shear at midspan. All right. Now, when the load is at 0, shear 0. When the load is at the 0.1 L, this picture, you know, somehow I can use this. It seems to be very lacking. Oh, it's better now. When the load is at this location, 0.1 L, the shear here is 0.1, but it's going up, you see? This is the proper free body diagram. Shear on the right goes up. According to the sign convention, this is negative. Correct? Can you remember this sign convention? Positive shear is like this, right? On the right must be down to be positive. So if you have the shear on the right that goes up, so it's negative. So at 0.1, you have shear equal to minus 0.1. Okay? And when we move to this, when you place this load at this location 0.2 out from the support, we have the shear in the middle equal to 0.2, but again, it goes up. So this is the negative shear according to the sign convention. Point 2, and then needless to say, when I place this unit load at the location 0.3 out, now I have the shear in the middle equal to 0.3, but it goes up. It's a negative 0.3. Up until I reach the midspan. Okay, when I reach the midspan here, you see, when I am right here at this location, here, you can see I still have 0.5 of this shear at midspan, correct? When the unit load is right here. Okay, so that means at midspan, this shear is also going up, so it's 0.5, sorry. It's 0.5 negative here. So that's at midspan. But again, at midspan, we're still at midspan, but this unit load moves slightly to the right of the line at midspan. If the load just moves only 1 nanometer to the right, what you are left with, this free body diagram, is this one, right? When the unit load moves, I should write it down. When the unit load moves slightly to the right, it means that the, oh, I still have more. It means the unit load leaves this free body diagram. So as a result, you have this instead. Now the unit load is just off, you know, it's somewhere around here, you know, but it's not on the free body diagram anymore. So you have this. Now the unit load is not on the free body diagram anymore. Correct? So in order to have the equilibrium on this free body diagram, I have to have the downward shear here. Right? I need to have the downward shear so that I have equilibrium. Shear is now downward to provide equilibrium. And you see, when you take the moment at midspan, you take the moment here, and when you take the moment here, the load is only slightly to the right, so fractionally to the right. So when you take the moment here, it's, you know, we can say the load passes through this point, so it's 0. So the moment remains the same, which is equal to 0.5 multiplied by 0.5 L, right? It's the same value. So when we consider the load, you know, slightly move away from the line here, the shear changes the direction, but the moment remains the same. So that means when your unit load reaches midspan, when it stays on this, the value is negative. But once it moves away one tiny bit to the right, your shear changes from upward to downward. And you see this sign convention, when your shear becomes downward, there is a sudden change of, oops, look like 0.5 again. And look like 5 again. Okay. So you see what I'm getting at? It's slightly sad that this is too small, but again, it's okay. And now I will move this picture later. And now you can see I can continue to move the load. Say, let's say at the unit load is at the location 0.7 L. See, just the same as this. Now I have when the unit load is at 0.7 L, I have the reaction equal to 0.3 P, right? Remember, I want the midspan shear. So I can use the free body diagram, like cut at the middle. So I now have this free body diagram, right? I know that the reaction is 0.7. I no longer have the unit load on it. So now this is, oh, sorry, not 0.7, 0.3, right? 0.3. So in order to have this under equilibrium, I need to have 0.3 downward here. Right? And I can do the same with the moment. The moment is now equal to 0.3 multiplied by 0.5 L, which is equal to 0.15, right? Yeah. You see that's 0.15, exactly as this, 0.15. So now you see that the shear will continue to go down. And in fact, it's just positive and equal to the value of the reaction here, right? So before that I finish, let me plot the influence line of the moment for you as well. Okay. When everything is at 0, it's at 0. No doubt about that. When the unit load is at location 0.1, moment is 0.05 L, and 0.2 is 0.1 L. It's kind of tiny. Okay. This is 0.1 L. And then you have 0.15 L. And then at midspan, you reach this value of 0.25 L. And then, you know, at this 0.15 L, it's at the location 0.3. When I move it to 0.7 here, which is sort of a mirror image, because if this is 0.3, 0.7 is, you know, the same distance from the midspan equal to this. And at this location, I have also 0.15. It's sort of, you know, give us a hint that the influence line of the moment should be, you know, a mirror image. So let me try to move this away to a better location. Okay, you should be able to predict that the influence line of the shear force at midspan will look like this. Okay, and the influence line of the moment at midspan would look like this. Should be a solid line, and then like this. Okay. So, you know, remember, this is the influence line. This is the line that shows you the change of shear at midspan of the beam with the load being placed on any location. Load, this load is of course the unit load. Okay, and this is the moment, of course. Moment. Okay, when the load is at any x location of the beam. So I can say that, okay, if I have the beam like this, oops, sorry. And I say I have the unit load at this location point. It's too tight. Say if this unit load is placed at the location, say 0.25 L. What would be the shear at midspan? I can just come to the influence line and say, okay, you want to know the shear at the midspan when the load is here. I can just, okay, 0.25 is here, right? This is 0.25 L. I can just come to 0.25 L because that's the location of the load. And then I can go ahead and look at the value. And now I know, okay, the shear at midspan will be equal to minus 0.25. Okay. And likewise, if the load is here at the location 0.25 L, I want to know how much moment at midspan of this beam is going to be. I can just come to this influence line and say, okay, here, 0.25, and I can read the graph. 0.25 L, so it's a half of 0.25, right? So I can just write it down from influence line when the load is placed. Sorry. At 0.25 L. From influence line, you can say that, okay, V is equal to minus 0.25. And excuse me, I should the admit span of this beam is equal to minus 0.25, and the moment admit span is 0.25 L, because it's right there at halfway, right? So I know it's a half of this, or it's equal to 0.125 L. So that's the creation and the use of the influence line in a nutshell. I would like to stop the video for the time being.